In this new video, we are going to step away from the functional equation we have seen before to analyze an interesting combinatorics equation. The combinatorics equation that we are going to prove here, we are going to prove that for any p strictly greater than n, the sum from k equal p to n of minus 1 to the power of k multiplied by n choose k multiplied by k choose p, this sum is equal to 0. And it may look a bit strange that for any combination of value p and n, as long as we have a p strictly lower than n, this sum will be always equal to 0. So one idea to prove this equality will be to use, for example, induction, because we have to prove this equality for the integer p and n. But it might be a bit difficult to prove that by induction, because not only we will have to do an induction on n, but we will also have to do an induction on p, and we might try to find something a bit clever than induction here. So one thing that we can start with is to recall the binomial theorem. And the binomial theorem is stating that if we have 1 and x, for example, and we take this to the power of n, then we can write that this is equal to the sum from k equals 0 to n of n choose k multiplied by x to the power of k. So we can see that we have a correspondence here between the n choose k from this equality and the n choose k here, but something is missing, and in particular the minus 1 to the power of k is missing. But we can actually get this minus 1 to the power of k if we write another formula, which is that x minus 1 to the power of n is equal to the sum from k equals 0 to n of minus 1 to the power of k n choose k. Okay, so that would be definitely a way to find the minus 1 to the power of k here, but it is still hard to explain how do we get the k choose p that we find here. How is it possible to get these two binomial coefficients multiplied by one another? And in fact, what we can notice is that this k choose p looks like it's something that is coming from another formula that would be, for example, the 1 plus x to the power of k, in which case we will have a sum that will be the sum from p equals 0 to k of k choose p x to the power of p. So the trick we are going to use is actually to kind of embed this formula inside that formula, and I'm going to explain in further detail what we're going to do. So the trick here will be actually to express a very simple polynomial that is x to the power of n, and to rewrite it in a much more complicated way. And this more complicated way will actually help us to prove the formula above. So x to the power of n can be rewritten as 1 plus x minus 1 to the power of n. Here the trick is very simple. What we are doing is that we are adding 1 here and subtracting 1 over here. And according to the binomial theorem, this is equal to the sum from k equals 0 to n of minus 1 to the power of n minus k, n choose k of 1 plus x to the power of k. Okay, and as we have seen above, we know how to express 1 plus x to the power of k, so we can write that this is equal to the sum from k equals 0 to n of minus 1 n minus k, n choose k, sum from p equals 0 to k of k choose p x to the power of p. So now we are going to put the sum symbol next to each other, and this is equal to the sum from k equals 0 to n of the sum from p equals 0 to k of minus 1 n minus k, n choose k, k choose p, x to the power of p. Okay, so here we start having a form that looks much more like the formula that we are having above. So it looks like we are on a good path. Now, what it will be interesting to get is to have a kind of formula where we have a coefficient for the polynomial x0, a coefficient for the polynomial x1, etc., up to a coefficient for the polynomial xn. But to obtain that, we need to put the sum that depends on p, because p is actually the power of this x. We need to do an interversion of the sum sign so we can have the sum that depends on p in front of this formula. So to do this interversion of the sum sign, what we can do is to represent on a graph the indices k and p and see how we can reposition them to do this sum interversion. So k is an index that has to go from k equals 0 to n, and p will eventually also reach n, but p must go from 0 to k. So if k is at this position, then p can only go up to this point. If k is at this position, then p can only go up to that point, etc. So at the end, the indices k and p are contained within this area. And so if we want to put in the front the sum that depend on the p index, then what we can see is that when p has a certain value, the k value can only take this value from p up to the value of n. So basically, writing the sum from k equals 0 to n of the sum from p equals 0 to k is exactly the same as writing the sum from p equals 0 to n of the sum from k equal p to n. Okay, so we can rewrite the formula here by the sum from p equals 0 to n of the sum from k equal p to n of minus 1, n minus k, n choose k, k choose p, x to the power of p. So this is equivalent to write this as the sum from p equals 0 to n of ap x to the power of p. And by identification, we see that the ap coefficient is exactly equal to that sum over here. But let's not forget that this polynomial is exactly equal to that polynomial, and so by identification, we know that all the coefficient ap with p strictly lower than n, all these coefficients are equal to 0. And so this implies that if p is strictly lower than n, then we have the sum from k equal p to n of minus 1 to the power of n minus k, n choose k, k choose p. This sum must be equal to 0. Okay, so it looks like we are very close to prove this equality over there, except we don't have minus 1 to the power of n minus k, we have actually minus 1 to the power of k. But this is not so complicated to get the same formula. The only thing that we have to do is to put the minus 1 to the power of n in factor. Indeed, because it doesn't depend on k or p, we can write that this formula is equal to minus 1 to the power of n of sum from k equal p to n of minus 1 to the power of minus k, n choose k, k choose p. And finally, we know that minus 1 to the power of minus k is equal to 1 divided by minus 1 to the power of k, which is exactly the same as writing minus 1 to the power of k. So we can perfectly replace the minus k here by k, and because we know that this is equal to 0, and we know that this part is not equal to 0, necessarily we must have sum from k equal p to n of minus 1 to the power of k, n choose k, k choose p is equal to 0. And that's how we prove this equality.